Hello, everybody. Welcome back to another discussion in dynamics. Today we'll continue kinematics of rigid bodies. And plan for today is following. We will start with a very brief lecture review and then two examples. So without further ado, let's dive straight into it. Let's do brief lecture review. So this is what I prepared for today. So I just would like to bring your attention to following situation. Let's say that we have a rigid body, exactly the same rigid body we had last time. And that rigid body has some shape. It has, we know where the center of mass is located. And we know that there are some, that our body is subjected to some forces and moments. So last time we said that if we sum the forces acting on our body, we can, they will result in in this expression, yes? That sum of forces is equal to m times AC, where C is center of mass. Then also, we can always do that. We can always sum all the forces and the moments about point C, and this will equal to IC alpha body. So this is always true. We can always do it. We can always write these two equations for center of mass. However, today we will talk about a very specific variation of what we learned last time. So if you localize, assume that you localized instantaneous center of rotation of our body. Then you can actually replace this expression with this expression. Yeah, I think that arrow is needed here. Yes, I forgot about arrow. Sorry, guys. Yeah. So basically, so that's actually all I want to say. Yeah. So anyway, if you find instantaneous center of rotation of our body, then you can write, then you can do sum of moments about that instantaneous center of rotation, let's say point A, and then that will be equal to IA alpha body, where IA is moment of inertia about that instantaneous center of rotation. For example, a pin. If you see a pin in the system, you can always consider writing this equation instead of this equation. Okay, I would like to underline word instead, because, for example, yesterday on Piazza, there was a question that people started solving homework 11, example 8, and they ended up with tautology, 0 equals to 0. Yes? This is because you wrote this expression and this expression. That's why I am not surprised that you ended up with 0 equals to 0. Okay, so this is also, it's not like super common, but it's quite common mistake on the exam. Yeah, so please don't do it on the exam. Yeah, so what I'm getting at is that you should go for either this expression or this expression. Don't go for them simultaneously, okay? Because you will end up with something like that at the end. And of course, IA can be obtained using parallel axis theorem, or in some countries, parallel axis theorem is called like that in US, and I think any English-speaking country. Yeah, in many other countries, it is called Steiner's theorem. So I'm going to use these both terms. Yeah, that's all. That's all. Was I clear? Yeah. Okay. Any questions? Okay. So what? So let's do some examples. Let's do example number 1. Example number 1. Please familiarize yourself with the problem statement before we start our solution. All right, so what do we have in here? We have this body of quite odd shape. And what do we know about it? First of all, we know that this is the location of center of mass, which is already good. We know geometry, yes, because we know that radius of this partial circle is r, and we know that mass and moment of inertia about c is m and ic. Yeah, this would be a symbolic solution. Plus, I think that they told us implicitly that there is no sleep, yes, at point A. Yeah, it is not stated in the problem statement, but I think that they require us to assume it. Otherwise, it won't make any sense. It won't make any sense. Okay, anyway, we will assume it. And what they ask us, and one more thing, things start from rest, so that's already good. And they ask us to find in part A to find alpha of the body, and then in part B to find minimal coefficient of friction to prevent sleep. Okay, let's start our solution. Since we are in kinetics of rigid bodies, we'll just follow our recipe again. Okay, so I'm gonna start with FBD and KD. And today I can do that something like that. I can copy and paste. Check this out. And I'm already done with my drawings of my bodies for my KD and FBD. Okay, I'm gonna go for easy forces as usually. So there is mg acting on our body. And in here we have normal force. And I also think that in here we will have a friction. Okay, I said I'm gonna go for easy forces. I went for all of the forces, yes? Okay, there are no other forces acting on the system. So now let's do KD. MACX. MACY. And this is our IC alpha, okay? Just for clarity, I changed my mind. It's not gonna be alpha body, it's gonna be alpha. Because we have only one body, okay? So it will be IC alpha. Okay, I think we're done with FBD and KD. Now equation of motion. So let's do sum of forces in the x direction, sum of forces in the y direction, and sum of moments about c, okay? So we will leave our new knowledge about instantaneous center of rotation for example number 2, okay? This example we will do like normal civilized people, okay, who take sum of moments about c, okay? Okay. What forces act in the x direction? Minus TF. And this is equal to MACX. In the y direction, we have two forces. Minus mg plus n. This is equal to MACY. And now moments about c. We have two forces rotating there, yes? We have n rotating in a positive fashion and TF rotating in a negative fashion. And this is equal to IC alpha. Okay, I think we are done with our EOM. So let's count number of unknowns. This is not known. This is not known. This is also not known. Oops. Oh, come on. I also think that this is not known. And alpha is not known as well. So unfortunately, we have 3 equations only and 5 unknowns. So in order to introduce more equations, we will follow the recipe we actually followed on Wednesday. So we're gonna go for acceleration analysis. Before acceleration analysis, are there any questions to what happened so far? About what happened so far? Okay, so acceleration analysis. So I wanna do acceleration analysis to actually, I wanna run two of them because actually we don't know anything about any point, yes? So we don't know anything about acceleration at point A, B, or C. So let's do acceleration B with respect to A and maybe C with respect to A. So in here we will have AB is equal to AA plus alpha times RBA minus omega squared RBA. Okay, and I'm just going to copy that expression and paste it one line below. Okay. But I'm just going to replace subscripts. I'm going to replace B with C. C, C, and C. Moreover, I kept in mind that our system starts from rest, so I can set this stuff to 0. This is 0, and this is 0. System starts from rest. Okay, so now let's just do acceleration analysis between B and A. So I'm just going to copy this here. And I know that AB has such components, ABX, ABY, and 0. However, I think that one of these components is 0, right? Because trajectory of this point, trajectory of B is here. This is trajectory. Right? So I think that this guy will be 0. Point B, acceleration at point B will always be horizontal. It's basically located in the center of the circle. Okay. And in here, at point A, we'll have such acceleration, yes, because we have no slip. No slip, yes? And also some of you already know that AY will be 0, yes? Because system starts from rest. Yeah, so there will be no centrifugal acceleration. But let's prove it, okay? 0, 0, alpha, and this vector right now. Orange, it will be orange, this one. So this is RBA. And you guys clearly see that this vector is 0, R0. Yeah, so if you do this determinant, you will end up with minus alpha R 0, 0. Okay, so we will end up with minus alpha R AAY 0. And you can see that based on the first component, we have that ABX is minus alpha R. And as promised, AAY is 0, which was expected because system starts from rest. Okay, so we have AB is equal to minus alpha R 0, 0, and AA is just 0 vector. Any questions to what happened so far? No, of course not. Okay. So let's do another acceleration analysis, this time between C and A. And let's use our findings from the previous acceleration analysis. Okay, so I am pretty sure that these two guys will be non-zero. ACX, ACY, and 0 is equal to 0 vector plus 0, 0 alpha times this vector, RCA. Let me draw it in the picture, RCA. Okay, RCA is here. This is RCA. So this guy has such components. Minus R, R0, I believe so. So this will be minus R, R0. Okay, and if you run this determinant, you will end up with minus alpha R, minus alpha R, 0. Great. So I think that these are two equations we were actually fishing for. ACX is equal to minus alpha R, and ACY is equal to minus alpha R. Yeah, because before we ended up with 3 equations and 5 unknowns, and now we found two additional equations. Yes? So yeah, I don't know. We are probably happy. Okay, so let's recap everything. So let's take these 3 equations. Let's take these 3 equations, and let's take these 2 equations. Oops. Okay, so we have 5 equations and 5 unknowns. Solvable, yes? And I bet that you guys know how to solve 5 equations and 5 unknowns. 5 linear equations, more or less, moreover, yeah? Okay, before I share with you the solution to that system of equations, are there any questions? Yeah. I don't know, I have like a little strange feeling that I'm talking too fast today. No, it's just a strange feeling, yes? We're on the same page, yes? Okay, cool, thank you guys. Okay, so this is the solution. So alpha will be equal to something, TF will be equal to something, N will be equal to something, ACX and ACY will also be equal to something. Let me see. So alpha is equal to 1/3 G divided by R. TF is equal to 1/3 mg. N is equal to 2/3 mg. And ACX is equal to minus 1/3 G, of course, and ACY as well. Great. Okay, but in part A, they ask us to find this thing only, yeah? Yeah, let me even scroll up the board. They asked us for alpha, yes? Heck yeah. Here. So we found it, yeah? Actually, one more step, yeah, because they ask us for the vector value. So alpha vector-wise will be equal to 0, 0, 1/3 G divided by R. And this will be a positive value. So it will rotate counterclockwise, yes? Which makes sense, because if I scroll up the board, you can see that our system will indeed rotate counterclockwise. Yeah, because this is our mg, is located here, and this is our support point, yes? So our system will rotate counterclockwise. So everything looks legit. Okay, so we're done with part A. Answer part A. And now in part B, they ask us to find mu s minimal So since we are in static friction range, we can write TF lower equal mu s n. Yes, because this is the inequality that governs static friction region. And my idea yesterday was to basically take these two findings and plug them in here. Yeah, and let's see what will happen. So we have 1/3 mg is lower equal mu s 2/3 mg, and some things are going to cancel out. Yes, I think that these three will cancel out, as well as mg. So you guys can see that our mu s is larger equal 1/2. So the minimum value will be obtained at the edge of that set. Yes, so our mu s mean is equal to 1/2, and this is the answer to part A. Part B, of course. Sorry. Okay, so for the 10th time today, are there any questions about what happened on the board? No questions, yes? Okay. So, do I want to say something? Yes, I will have a question to you guys. So that it's clear. Yeah? This is the solution to the problem, yes? However, can you detect, are you able to detect instantaneous center of rotation of that body? Question mark. It's a question. Yes. Yeah. Ian? Excuse me? No, not really. Yeah. Yeah, that's. So I'm not sure if I'm able to answer that question, but I see your point. So actually, your answer is incorrect, because when it comes to motion, we kind of consider what happens at this instant, yeah, but also what will happen in a second, you know, yeah. So what you said that no, because it starts on rest, because you focused only on the current time instant, yes. However, this thing, there is no sleep in here, yes, and that thing rolls, yeah. So actually, we are able to find instantaneous center of rotation, yes, which will be pointed by Tom. Is it? It is A. Yes, exactly. Yeah. Was my answer okay? Yeah. Cool. Yeah. Thank you for being active. Yeah, I really appreciate it. Yeah. So okay. So if you want at home, I can give you extra homework, but you don't have to listen to anything I say actually. So if you want at home, you can actually solve that problem one more time, but instead of writing this expression, forget about that one. You can actually write sum of moments about A. Okay? And you will end up with exactly the same solution. Yeah. So, so actually we can do it. Yeah, because this approach will actually be much faster. Yeah, because there is only one force rotating about point A. Do you see it? Only one force is rotating about point A. Yeah. So it will be minus mgr, I believe, and this will be equal to IA alpha. And here you must use parallel axis theorem to find IA, yes? So yeah, so if you want, you can solve that problem one more time using this approach, yeah? And you will end up with exactly the same answer. And by the way, why is it faster? Why this approach is faster? Because now we have everything on the left-hand side is known. Look here in this expression. We know all of these values. In contrary to what happened here, we don't know N and we don't know TF. Do you see that? So actually obtaining alpha via this approach is much faster. Yeah. Okay. So that's all I wanted to say. Yeah. Yeah, that makes sense. Yeah, because if we like sum moments about this point A, then we just get rid of all of these unknown reaction forces. Yeah. Yeah. So keep that in mind. Yeah. And for God's sake, please don't use these two expressions simultaneously. Okay. Go only for one of them. Okay. So that's why I'm going to erase this one. Okay. Yeah. Okay, only one of them. Okay. Yeah, I think that's all. I don't want to say anything else. Can we do example number 2, or are there any questions? Okay. So this is example number 2, and as usually, please read and understand the problem statement before we start our solution. Okay, so what do we have in here? And while I am talking, you can think on whether you're gonna vote yes or no. Okay, in our little poll, or maybe you don't want to vote at all. It's also fine with me. So anyway, what do we have in here? Aha, we have a beam in this configuration. And what do we know about that beam? Aha, we know the location of point of center of mass. We also know the mass and moment of inertia about C, and also we know length. And we are very happy that system starts from rest, yes, because it will simplify the problem tremendously. We'll see. Okay, and the question is where to put that pin A, or where to put that pin A so that our angular acceleration is maximum. Okay, so how far from the center of mass we should place that pin so that our angular acceleration is maximum. Do you understand the problem? Yeah, of course you do. So let's vote, okay? If you want to, if you would like to. You don't have to, yeah? But it would be cool if you do. And also for you, those of you who are watching this video, you can pause the video right now and think of your vote. So do you think that maximum angular acceleration will be obtained when we put this pin A at one of the ends, like presented in this picture? Yeah. If you vote yes, you can put your hand up right now. Yeah. Okay. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yes, 13 people. 13. Okay. So the 13. And no, if you vote no, put your hand up. 1, 2, 3, 4, 5. And if you don't care when somebody asks you to put your hand up, put your hand up. No, 1. Okay, great, great. Okay, so one of these 5 people, or maybe 2 or 3, or maybe 5 of these 5 people, can you please tell me why you voted no? Yeah. Why did you vote no? Do you mind sharing your thoughts, Kevin?
It seemed to be easier to put at the end.
Hey, 100%. Exactly. This is the answer I was looking for. Great engineer. Exactly. It's like psychological approach to engineering. Very nice. Okay. Anybody else? Okay. The remaining 4 people. Kevin, you don't say anything, please. You were right. It's no. The answer is no, by the way. I was wondering if you can tell me what was your thinking process. Okay. So let me show you why no, yeah? And this is, by the way, this is proof that democracy does not always work, yes? Yeah, that's true, yeah. I actually have a theory that democracy works only in one case, food, yeah. Because if there is a restaurant and you have a huge line in front of the restaurant, that probably means that they serve good food, cheap, and big meals. In, in my opinion, yeah. And I'm not a big fan of. I mean, okay, they will close my YouTube channel, so I'm not gonna continue. And let's continue. This is dynamics. Yes, this is not Michael's wanderings. Yes, let's continue dynamics. Let's solve that problem. Okay, let's solve that problem. And since we are in kinetics of rigid bodies, let's do FBD. Oh, sorry, FBD and KD. Okay, so I'm gonna draw this bar and center of mass. And I'm just going to copy it here. So, okay, I'm gonna go for easy forces. So I'm gonna go for mg. I do not want black color. I want blue color. mg, and there is also reaction force, yes, at point A. Yeah, and I usually name reaction forces after name of points. So in here I will have ax and ay. Okay, and in here we'll have MACX, MACY, IC alpha. Okay, we're done with FBD and KD. I don't think that there are any other forces acting on our system. So now let's do equation of motion, okay? So let's do sum of forces in the x direction, sum of forces in the y direction, and this time, as promised, sum of moments about A. Because A is a pin, it's clearly instantaneous center of rotation, yes? We can do that. So what do we have in the x direction? Aha, only one force, yes? AX is equal to MACX. In y direction, we have AY minus MG, and this is equal to MACY. And now, how many forces rotate about A? Only one. So it would be minus MG H, right? Because that distance was defined as H. And this will be equal to AI alpha, yes? Not AC, but AI. I'm just gonna even make it red so that you guys remember. Or like at least you pay attention to that subscript. Okay, so let's use Steiner's theorem to find AI. IA. Sorry. Plus mh squared, right? Because this is IC plus m distance squared. So that will be 112 ml squared plus mh squared. So that will be basically m 112 l squared plus h squared. Okay, and now let's plug this thing in here. And I also think that we don't need these two first equations, yes? To solve for alpha. Yeah, they ask us to find the maximum alpha, so we can actually ignore these first two expressions. So now we will end up with minus mgh, and this is equal to m 112 l squared plus h squared alpha, yes? And m cancels out. So we just found expression for alpha. alpha is equal to minus 12 GH L squared plus 12 H squared. I just don't like fractions. Okay, so I just put it like that. Cool, so we actually found alpha expressed as a function of H. Alpha expressed as a function H. Okay, how to find the maximum of that function then? Yeah, they ask us to find H such that alpha is maximal. And you know that, yeah, in your calculus classes, how did you find the maximum value of function of fx? Take a derivative and equal it to 0, yeah? So we are just going to do d alpha dh, and this must be equal to 0, yes? This is our requirement. Yeah, so let's do that. D alpha dh, and if I remember correctly, this will be L squared plus 12H squared square minus 12G times denominator minus numerator times derivative of denominator, right? Times 24H. Cool. Okay, and this must be equal to 0, yeah? So this is equal to 0 when numerator is equal to 0, yes? And by the way, our the denominator cannot be 0. It is always positive value, so it's great because we cannot divide by 0. Okay, so I can copy the numerator here, and this is equal to 0, and I think that some things will simplify here, yeah? So we will have here minus 12G L squared plus 12H squared plus 12G H squared times 24. But these things cancel out. That 12 can be cancelled out. This G even. And we will actually end up with such expression, minus L squared plus 12H squared is equal to 0. Great. So that means that our H squared is equal to L squared divided by 12. Take square root of both sides, and you will end up with H equal either to L divided by square root of 12, or H can also be equal to negative of that. Okay. So far so good? Yeah. So we obtained two values, yeah, which is actually not surprising because there is a symmetry in our system. Yeah, there's a symmetry in our system. Yeah, I will get to that later, okay, in a second. So I mean maybe right now. So basically our pin can be either on this side, yes, and we will have such acceleration, or we can also place pin symmetrically on this side, yes, and we'll have acceleration this way, yeah. That's why we obtained two values, yeah. Okay, oops. So we just found the location, and by the way, you can already see that this is not at the end of the beam, yes, because if we obtained L divided by 2, then it will be that it would mean that our pin should be placed at the end of the beam, yes? L half, the answer L half will be telling us that. Okay, but now let's find alpha max. So I just must take this expression. I must take this expression, and I must plug this value in order to obtain alpha max. H is equal to L divided by square root of 12, right? So we will have in here minus 12g L divided by square root of 12, L squared plus 12, L squared divided by 12. This cancels out. So this will be equal to minus 6 divided by square root of 12, g divided by L. And if you grab your calculators, you will end up with such expression. It can be simplified. So our alpha, so this is actually equal to minus square root of 3 GL, G divided by L. Okay, so our alpha max is equal to minus square root of 3 G divided by L. For this case. For this case, yes? Why you are not listening to me? I'm talking to my laptop, sorry. But for H equal to minus L divided by 12, yeah, so for the other case, we will end up with alpha max positive, yeah, plus square root of 3 GL. Okay, so we actually solved that problem, okay? So let me just draw some, and we still have time, yeah? Okay, so let me just draw one drawing, summarizing everything, and then we can think maybe together why placing it at the end is not going to do the work, okay? We can think together. So this is our answer. Let's do these two drawings. This one was terrible. Okay. So this is our first case. So we can either place our pin here, and this distance is L divided by square root of 12, and we will end up with alpha max equal to minus square root of 3 GL. And this is clockwise, yes? Great. So that's why it's negative value here. Yeah? Or we can also place our pin here, where this distance is again L divided by square root of 12. But this times our alpha max will have same magnitude but opposite direction. Alpha max is equal to square root of 3 GL. Okay. So I forgot about saying one thing in my previous video. So if you want to have additional homework problem, you can always solve that problem once again, but this time, instead of writing this expression, you can do sum of moments about C. Okay? You can sum of moments about C. But then you will end up here with unknown. Yes? In here you will have minus AY H, right? IC alpha. Yeah? So that would be much longer. Yes? Because please observe that in here, everything in our left-hand side was known. Do you see? That's why that problem was so fast to solve. Yeah. But if you go for this approach, unfortunately, you will have to exercise a little bit to find AY. You have to find a reaction force. Okay? If you want to, you can solve that problem. I prefer to do it in this way. Okay, we have like 4 more minutes, I believe, yeah? So, is there anybody here who had like a light bulb appearing above his head and who can explain me why no is correct answer in this poll? Ian.
I was thinking about
Yeah, okay. That's a very, very good way of thinking, yes. And probably it's a correct answer, yes? Tom, you wanted to put your hand up? No.
Yeah,
Ah.
similar. Like if you put it at the end, you have like more mass is further away from the point, so it takes longer to accelerate.
Exactly, perfect. Exactly, yes. So it's a trade. In other words, it's a trade because I know, guys, so there was 13 people who voted yes. And I know why you voted yes. You voted yes because that was your process of thinking. The farther you place the pin from the center of mass, the larger the arm will be, the larger the moment will be that can rotate our body. Yes, that's why you voted yes. Yes. However, and that's a good idea. However, also when you place that pin farther from the center, you have larger moment of inertia about that pin. So not only arm of the moment increases, but also moment of inertia increases. And the larger the moment of inertia is, the harder it is to rotate the body. So it's actually an optimization problem. Yes? And you were asking like a couple of months ago, Ian, if we're gonna do optimization problems. Yes, we are gonna do optimization problems, yes. Yeah, so that would be my answer. Was it clear? Yeah. So anyway, wait a second, guys. So for example, if there is like very heavy body, yeah, it's hard for me to push it. Yes. Yeah. So also, if body has a large moment of inertia, it's hard for me to rotate it. Yes. So this is exactly the case in here. We increase the arm h, but also with that h increasing, our moment of inertia about that pin increases. Yeah. That's why the golden point of putting that pin is somewhere in between center of mass and end of the beam. Yeah, that's why. Okay, thank you for today. I hope it was clear, and I hope to see you next week. Bye bye.